forget I'm recording it. All day. All right then. So yeah, a proton donor and a base. Obviously the opposite. It just means you don't have to have OHs necessarily. So that's for now. When you do transition metals, if you haven't already, you might do the Lewis acid.
Yeah,
base.
we're not done that yet.
We'll worry about that later. Strong acid and strong base, we've got to define those. So what is a strong acid? And it's nothing to do with concentration.
So like how much it ionises the solution?
Yeah, how well it ionises completely.
Completely, okay.
Strong acid. So can you think of a strong acid? Like I say, it could be dilute, but it's still a strong acid.
I want to say hydrochloric acid.
Yeah, why not? And that, if you put it in water, it's actually a gas. For reasons that we discuss one day. Plus aqueous just means water. Yeah. H plus and Cl minus. And it completely dissociates.
Okay.
That's what that's called.
So that's the whole ionisation?
Yeah, that's a strong acid. And let's try a strong base.
I don't know a strong base.
Anything with OH in it, really.
Like sodium hydroxide.
Yeah, so that's going to dissociate completely as well. Yeah, this doesn't come through this time. That'll be a solid.
Yeah.
Put it in water and it will completely, there won't be any sodium hydroxide left. It will just be sodium ions and OH minus ions.
So that's the base?
Yeah.
Okay.
So I'm going to put that there and there. So that's what it does, and they're both aqueous. There's a way to calculate the pHs of strong acids.
Okay.
Do you know what that method is?
Nope.
All right, well, we might as well do it. That's what we're here for. So let's try 0.04 moles per decimeter cubed of HCl, maybe.
Okay.
What you do is, you've got the concentration, you need to use this little expression, which you've probably seen. If you haven't, you're going to be using it a lot.
Okay.
Minus log, much easier than the Arrhenius equation.
Yeah, no, I've not
Really?
seen this yet, no.
It's amazing. But it's very simple, as you can see.
Yeah.
So, what do the square brackets mean? You know that.
Yeah. Is this for going to that equilibrium rate?
Well, it doesn't matter. The square brackets mean the same in either. It's the only thing they have got in common, really.
Doesn't that just mean what pirates do?
It's just concentration.
Oh, is that just, okay.
Yeah, that's worth knowing. So all you have to do to find the pH is simple. You just do minus log H plus concentration, which is what we've been given. I don't think you're going to get a question quite as simple as that, but if you take minus log of 0.04.
To put that on a calculator?
Yeah, I think it's going to be 4, isn't it?
So where's log minus?
You just do minus that sign.
Yeah, and then put log.
Yeah, not natural log, just
normal log, and then 0.04.
Yeah, I'm allowed to say things like 0.
So have I got to put another bracket on the end there?
You might as well, just to be sure.
1.39.
Right, so 1.39.
Yeah, 1.397. So.
Quite low.
Yeah.
Well, you wouldn't be surprised, would you, if you did that?
So what is that as pH?
Yeah.
Okay.
No units. So why do we use logs? Well, it's because a pH of 1 is so tiny compared to
Yeah, okay.
Sorry, so large in terms of H plus. So pH, if we draw the pH scale, there's a big lag on this pen. I might start using paper. So pH, what's the scale go from?
From 1
to.
Oh, is it 14?
It goes up to 14.
Yeah, I was going to say
it seems like a strange number, but there's a very good reason for it. Why it's 14, and we'll hopefully find that out today. We'll go through it. So a pH of 2 goes up by a factor of 10.
Yeah.
So 2 is 10 times.
Yeah, 10 times the 1. Okay.
And 3 is 100 times the 1.
But 10 times 2.
Yeah.
Okay.
But it's just 100 times more. So, and that would be 1,000, 10,000.
Yeah. Keep going on.
Yeah. That's why they use it, so you can fit on a graph a very wide range of pHs, because otherwise it'd just be a ridiculous scale. And that's all you do for that one. Just one more strong acid. What about one with more than 1 proton in it? Or the ability to produce more than 1 proton. In other words, a diprotic strong acid, maybe.
How to calculate the pH, really?
Well, just choose an acid first, and then we can do that.
I don't know.
What about sulfuric?
Oh, true.
Now, this is slightly different because it's got 2 H's in it.
Mm-hmm.
And we're not drawing equilibrium signs at the moment, are we? So that's plus AQ as well. So what's that going to dissociate into?
Would it just be 2H+?
It'll be 2H+, which is significant.
And would your SO4 stay together?
They will, yeah. People struggle with that for some reason. They start dividing it up into different atoms. That's just an ion. Mate, it's covalently bonded in there, but it's an ion.
And it's 2 minus.
So we start with 0.04.
Yeah.
Just arbitrary number. Now that's the concentration of the sulfuric acid.
Okay.
But that is not the concentration of the H+ this time, is it?
So, I don't know
what it is, if you had 0.04 moles in decimeter cubed,
that's of the whole solution.
you would actually get twice as much of a concentration of H+.
Why is that?
1 mole of that
Yeah.
produces 2 moles of these.
Okay.
So that would be.
Okay.
So that's the concentration of that. Square brackets just the same. And that's the concentration of the H+, which would be 0.08.
Yeah, which is double.
And if you put that into the calculator, we should get an even lower pH.
Let's have a look. Minus.
Maybe less than 1.
1.09.
Oh, right. Just about 1 then.
Still lower.
I'm not very good at guessing. No units. It's just a pH scale. Once you take the log of something, the units are gone anyway.
Okay.
Bases are a bit harder to do, but we won't do them yet. We'll do those later. So that's strong acids.
Yeah.
Straightforward.
Okay.
Very straightforward. All we need to do is weak acids.
Okay.
See, it's writing properly now. The light's gone. So I'll stop writing like a 4-year-old. Right, what do weak acids do or don't do?
So they just don't fully ionize.
That's it. So you do know some of this. How do you know?
That's just from GCSE.
Really? Just covered that?
It was more just like a touch thing.
Well, let's choose one then. Any weak acid. Usually organic.
I don't know.
All right then. Methanoic.
Okay.
Have you done carboxylic acid?
Yeah.
What's methanoic then? It's got 1 carbon.
Methanoic. Let me draw it, sorry.
I tend to go off to other topics as well to try and keep everything holistic.
So CH H.
Yes, so we can write it as C.
Yeah, OH.
And if you put that in water, I won't put the AQ in.
So is this one? So is it not reversible for strong?
No.
No. Okay.
Some people that study it all the time might argue that it is slightly in equilibrium.
Okay.
But for all intents and purposes, they dissociate completely, and these hardly dissociate at all.
Okay.
So which hydrogen is it that's going to come off? Because that's covalent.
Yeah.
So which bond's the weakest one? The last one, yeah. So you're going to get HCO. What we need to put on that? Minus.
Yeah.
I hope this isn't too basic.
No, it's fine. No, it's good to go over it.
And what you do next, and there's a lot of repetition from what you did with strong acids and equilibrium from weeks just gone by. We're going to write an expression for Ka.
Okay.
But it's no big deal. It's not a new thing to learn because Ka is basically Kc.
And this one's the same rules as doing it for equilibrium.
Yeah.
So your product's on the top.
Yeah.
Okay.
So we put that in square brackets. We put the H plus in square brackets.
And on the bottom.
And the acid on the bottom. And we make a couple of assumptions as well here. We assume that when you put this in water, it only dissociates a tiny little bit.
Okay.
From when you start to when you put it in water, this isn't going to change hardly at all. These are going to be very small.
With a small pH?
A very small Ka.
Okay.
I don't know what it is for methanoic acid. It's something times 10 to the minus 5, so it's small.
Okay.
Might even be 10 to the minus 4. So a weak acid only partly dissociates.
Okay.
This is a reversible reaction. And when it reaches equilibrium, the forward reaction and the reverse reactions are happening at the same time. But because Ka is so small, there's not going to be much of this at all.
So what's my Ka again?
It's just the equilibrium
rate.
constant.
Okay, yeah.
Nothing to do with rate.
Okay.
It's only to do with equilibrium.
Okay.
That's why we're including the reactants and the products.
Okay, cool.
The problem is most questions are like this, like what we just did. 0.04 moles per decimeter cubed again. That was just fished out of thin air. That's the methanoic acid concentration.
Yeah.
And as you can imagine, we can't just use that in the equation. It's not possible. Because the H plus is going to be much, much less than that.
Yeah.
Fraction of that, tiny fraction, because this is small. But because we've got this, we can calculate what H plus is, and therefore we can calculate the pH. Trouble is, what do we know? We know this. We'll make one up.
Yeah.
I don't know what it is. 1.1.
Okay.
That's a 5.
Yeah.
So we'll say we know that. We want to find this.
Yeah.
Then we can find the pH.
Okay. We know the bottom one.
We know that. Trouble is, we don't know this.
Okay.
So that's 2 unknowns. The one we want to find and something that we don't know about.
Okay.
There are ways you could find that, but it's not necessary because 1 mole of that, if it's pure, will always produce 1 mole of that. 1 mole of that.
So it's just like half.
Well, what you can do is you can square that because that's that times that.
Okay. Oh, so it's basically the same value.
Yeah.
Okay.
So what we can do is, if they ask you for a value for Ka or an equation for Ka, you'd have to write that out.
Okay.
You can't simplify it until you've done that first. So they want to see that you know what Ka is. This isn't really Ka. This is a derivative of it.
Yeah.
So we can just square that.
Okay.
And after that, it's a case of just putting numbers in.
Okay.
Find H plus. It's as simple as that.
0.001 times 4. So you get 4.4 times 10 to the minus 7.
With the pH.
I've just done that times that.
Well, what you need is,
what do I need to...
we don't know what that is.
Yeah.
What we're trying to do is rearrange that for H plus. So what would that be?
Just square root it.
Square root of Ka times, I don't know why it suddenly turned into ethanoic acid.
So do I just need to square root my answer?
Yeah.
Okay, so it's 6.6 times 10 to the minus 4.
It's not very low, is it? But that's fine. That's how you've done it. So
What do you mean? I don't know. I think 6.6 times 10 to the minus 4 is quite low.
Oh, sorry, we haven't logged it yet.
Oh, okay.
So it's going to be less than 4. Can you just log that? It's just going to be 3 points.
So do I just click what?
If you do minus log and then press the answer key.
Minus log answer. 3.17.
Right, so the pH is much lower than, much higher. 3 points something.
So is it meant to be higher for weak acids?
Yeah.
Okay.
Because they don't have as many H plus ions in solution.
Okay, yeah.
Because they don't dissociate, most of it stays like that.
Okay.
I don't know what it was, but that's not necessarily right anyway. And the other thing is it suddenly changed from methanoic to ethanoic. There's no significance in that apart from I'm stupid and did that by accident.
It's alright, don't worry. I knew it.
There's another thing called pKa, but that's nothing to write home about really. It's just minus log Ka.
And what's pKa?
It's something that we may use. I don't know what you call it actually. Just pKa.
Okay.
So if you were given pKa and you wanted to find Ka, it'd be 10 to the minus pH. No, pKa.
Okay.
I haven't got any questions to do with that yet. I've got one loaded up somewhere. Is that all right for weak acids?
Yeah, no, that's fine.
If you can do that, you can do it for any acid. The acid might change.
Yeah.
Ka might change.
If do you know the top ones, if these were at different moles, how would you do it then?
If what were?
These the products.
They can't be.
Can they not? Okay.
If a mole of that, if one molecule of that, in fact, decides to dissociate, because some of them will.
Yeah.
You're only going to get one of those, and you're only going to get one of those.
So it's not possible to get
No, as long as it's pure and the water's pure.
Okay, cool.
Because obviously if there's some acid already in the water, it's going to be meaningless. So you need to be able to do that, simplify it, and rearrange it, and try and not change the acid into something else. Like I've done so for anyone that's watching, I've sorted it, right? Okay. Any funny messages? All right then. What else? We briefly talked about pKa. Briefly, techniques and procedures to measure the pH. What would you do for that?
Technique?
Yeah.
Is that not just the equivalent?
No, how do you actually measure it to prove that you've got it right?
No, I don't know.
Well, you could use a pH meter.
Yeah.
That's all I'm on about.
Okay.
Or maybe universal indicator, but that's not very accurate.
Yeah, I was going to say, because we just use the dye, but no,
it's all right. That's it. So we've done strong acids, we've done those. Now, strong bases are a bit more difficult. We've done weak acids, so what have we done? What haven't we done? We've done this. You have to be careful if it's got 2 H's in it, you have to double the concentration.
Okay.
And if it's H3PO4, you have to treble it. Because that's going to give you 3 times. It's unusual to get that one, but you never know.
Yeah.
So we know what pH is, we've got an equation for it, you know how to find Ka. You can find the concentration from any 2 others. In other words, if there's only one unknown, you can do it.
Yeah.
Buffers, a bit more difficult. We'll do them in a minute.
Okay.
But the next thing to do is KW. Okay. So you haven't written anything down, so I presume you're just going to use this.
Please, yeah.
Is that all right?
Yeah.
Watch it. Watch it as many times as you want. It'll still be there in the summer.
No, that's handy.
It is. I mean, some people don't like the idea.
No, sheets might get lost.
I've got one student who will not even let me record it. Never mind with pictures and voice. She doesn't even want a name on it. Never mind anything else. So, all right then. Buffers we'll do in a minute. KW next.
So what's the difference between Ka and Kw?
Well, that's we'll go through that. The thing is to do with, it's called the ionic product of water, which is a bit long-winded for what it is. Water is actually a weak acid.
Okay.
Pure water is actually a weak acid. Which seems a bit strange, but it is. Not only that, that means it dissociates. So in some water, some of it will be in solution as ions rather than just a liquid. Well, if it's got H plus ions, it's going to have a pH. It doesn't matter what the OH is. If that's more than, if that's higher than, to give you 7, then you can still get a pH of less than 7 for pure water.
Okay.
So what we know what Ka is, don't we?
Yeah.
It'll be that and that multiplied.
Yeah.
Over that.
Over that. Okay. Yeah.
But because this is so small, Kw is actually a minute number.
Okay.
It's not as small as the Avogadro constant or anything like that. But it's 1. It's like writing in treacle-less. Let's just slow it down. I might have to stop the video. Right, so just 10 to the minus 14.
So that is Kw. Okay.
I need to work out what the units are. It's going to be moles per decimeter cubed, isn't it? Well, it's not, because Kw, we haven't even said what it is
yet.
Okay. Kw is this. It's H plus on there, and OH minus, and that's it.
So it's not over the reactant?
It's not over water, because water is present in a large excess at the start and after it reaches equilibrium.
Okay.
So that's large and constant. So we can discount it. But when you take things out, you can't just make them disappear and then forget about them. Might be convenient, but we can't. So that's why it's not Ka anymore, it's Kw.
Okay.
So we know what that is, and we know what that is.
You can work out here.
Very easily. For strong bases, you don't have to do calculations for weak bases, I don't think.
Well, I don't know what OH is.
Well, that's going to be whatever alkali that you decide to add to it, or at base. So sodium hydroxide.
Yeah.
So we'll use 0.04 again. Now then, all you have to do, you can't make these equal, because they're not going to be. You've just banged a load of this in.
Yeah.
So there's hardly any of this. So the OH minus is going to be much higher than the H plus.
Okay.
And we know what Kw is. That's at 25 degrees C. And we'll talk about what happens if you make it hotter than that.
Okay. So if I was going to work this out now, would I literally just put that number in and that number? So
it'd just be Kw over the OH minus.
Which is just 0.04.
Yeah, because it's only a mono hydroxide.
Okay.
So can you work that out? We should get a high pH.
On the calculator, so 1.1 times divided by
Divided by 0.04, yeah.
Was it meant to be high, did you say?
Yeah.
Let's put that in brackets.
Well, it'll be 10 to the minus something.
Oh, so it's 2.5 times 10 to the minus 13.
Right, 2.5. Sounds a bit weird, doesn't it, when you've not done it before, but that's perfectly fine.
Okay.
Because I can tell by looking at that.
So is that a pH?
Not yet, because that's just H plus.
Yeah.
But we can soon get to pH, can't we? I can tell from looking at that, it's going to be around 13. It's going to be between 12 and 13.
Okay. Just for
probably nearer 12 and 13.
Okay.
So if you minus log that, you should get 12 points something.
Minus log 12.6.
Okay. Now that sounds reasonable, doesn't it?
Yeah.
For an alkaline solution, basic solution. So that's really easy. We have to know the assumptions that you make. You assume that's constant and big, so you ignore it.
Okay, so that's the pH of water or the pH of H?
That's the pH of a solution
Okay.
of sodium hydroxide.
Okay. So this isn't got anything to do with water.
Well, yeah, you're going to put that into water.
Okay.
To make a solution of that strength.
Okay.
So that's what we've just done there. So we've done that, and we've done weak acids.
Okay.
Is that okay?
Yeah. No, yeah, that's good.
They'll always give you a KW. And that's why KW, that's why the pH scale goes up to 14.
Okay. Is that because that's the big, okay.
So if you minus log that, you'll get 14.
Yeah.
So what does neutral mean?
Is that just pH of 7?
That's what people think, yeah.
And is it not?
Well, neutral just means that you've got H plus and OH minus at equal concentrations.
Okay.
Which is what you would get, isn't it, in pure water? That's totally neutral now, isn't it? That's not meant to be a squared or anything like that.
Okay.
So H plus is equals OH minus in pure water. Doesn't mean the pH is 7 though. We can see about that. At room temperature though, it will be. So how can we calculate the pH? So KW is the same as it was before. And it's one of those, there's only 3 things in it, so it's not good.
So we're not adding anything to it this time?
No, just pure water. I'd write that down. So we haven't added any sodium hydroxide.
So would you just divide that KW by 2?
Well, what this is KW time equals that times that.
Yeah.
Well, if you know, all we've got is water.
Yeah.
At 25 degrees C. So what do we know? We know that.
Yeah.
Because it's 25. That's what we want to know. So we can find the pH.
Yeah.
That we don't know. Well, once again, we've got 2 unknowns. That's no good.
So you just square it?
Yeah, so KW, and after all, it's pH that we're trying to find, not anything to do with that. That's it. So the pH of pure water.
It's just the square root of KW.
Yeah, which is 1 times 10 to the minus 7.
Which is technically
7.
neutral at
yeah.
room temperature. Okay. That makes
well,
sense.
it's neutral. Pure water's always neutral, but it doesn't necessarily have a pH of 7.
Yeah, but pH 7 at room temperature.
Yeah.
Okay.
Now, when you get hotter, I should say that KW, as Ka is as well, is endothermic.
Okay.
What does that mean?
So it's giving off energy.
Is it? Endo.
Oh, and sorry.
Yeah, that's the right graph.
Yeah. Is it not? Is it taking?
It's taking in energy. Yeah.
Okay, yeah.
So what will happen to KW if we heat it up? Increase temperature. Let's make it 30 or something. don't know what the real answer is, but is it going to go up or down?
The KW?
Yeah. If it's endothermic, the equilibrium,
If you increase it.
It will go up.
Yeah.
And Ka will go up as well.
Okay.
If it's endothermic, which it is. We'll say that Kw is something different. Like 2 times 10 to the minus 13. I don't know what it is. So that's higher than it was, isn't it? So if you take the square root of that and minus BHG.
2 times 10 to the and then do I need to log that?
Minus log it, yeah. It's minus log so that we get a positive answer.
Yeah. 8.3.
So that's pure water, and yet it's neutral.
Okay.
Because H plus is OH minus.
We'll just go back to this again, sorry.
Yeah.
So where's this come from?
I made it up.
You just made it up?
I know it's going to be more than 1 times 10 to the minus 14. I don't know.
Because it's increasing, because that's increased.
Because it's
the temperature.
endothermic.
So what if we lower the temperature?
Then
that
you'll
goes
get
down.
Well,
Okay.
the pH will go up then, won't it?
Okay, yeah.
Because Ka will go up. No, Ka will go down, and Kw will go down, won't it?
Okay. Right, yeah, that makes sense now. I was a bit confused on that.
So that's Kw. There is another way of doing it.
Okay.
pH plus POH equals 14. Now POH, what do you think that is?
Is that just in regards to the OH?
It's a log again, yeah. Instead of H plus, it's minus log H plus. Oh, H minus, sorry. Start again with that one. So it's just a bit slow again. So POH is minus log to the base 10 of OH.
Right.
You know, when students laugh at me because I'm writing, I just say, you try writing on it, it's slow. So it's minus log OH minus, that's the only difference.
Okay.
So what you could do, if you've got 0.04 moles of sodium hydroxide, moles per decimeter cubed, and AOH, you could use that method instead.
You just put minus log 0.04.
Yeah, so you could find POH and you could
then take that away from 14.
Exactly, and you should get exactly what you will get the same answer.
Right, let's try it out. So minus log 0.04. So that's 1.4. 1.4 is 12.6.
Which is what we got before.
Yeah. Okay.
Most people do it the other method. But you can do this, you still need to know what KW is.
Yeah.
The thing is, I would learn one or the other.
I was going to say, this one seems easier.
Seems easier, doesn't it? Most people choose the other one, but I would choose that one.
It just, yeah, that just seems a lot easier.
Yeah, all you have to remember is that then.
Yeah, pretty much.
Because they'll give you that. But you're probably going to need to know what the ionic product of water is anyway.
Okay. Well, do you know how this one, your temperature?
Yeah.
Like, obviously that changed, that would, this not, how would the temperature come into that one?
Well, what happens when you increase the temperature? The OH and the H plus increase.
Okay.
So obviously KW increases. So at a different temperature, you're right. Yeah, you'd have to do it differently. This is only works at room temperature, really.
Okay. So it's just, okay, so just keep that in mind.
But they could give you a different Ka.
Yeah.
Then you'd have to put whatever the power is there. But it'll be that if you can use that one.
Yeah. Okay.
Right. So that's K. That's all of that lot. Now the only thing left, which is the hardest bit, is this. Yeah. How they work and the calculations.
Okay.
But they're based on weak acids. Notice there's no basic buffers. Oh goodness. They used to try and put that on the syllabus. Where is it? It's not it there. We'll go to the whiteboard then. Don't need the specification anymore. Right, buffers. It looks like a tiny little topic, doesn't it? But there's quite a bit to it.
Yeah.
To get it right.
Okay.
Should we base it on ethanoic acid? Because if we don't, I'll probably end up writing methanoic.
That's fine.
So it's straight back to this. There's not much new stuff to learn, but there's quite a bit of understanding.
Okay.
So that's ethanoic acid.
Yeah.
Weak or strong?
Weak.
So we need the equilibrium sign. We can't just do a normal arrow.
Yeah.
And it splits up. He's writing fast on the whiteboard. It must have been that document.
Yeah. Okay.
It's like before. So you could write an expression for Ka.
So is that a buffer?
Not yet.
Okay.
And we ought to talk about what buffers do. They resist small changes in pH.
So is that what they mean when you say it maintains pH?
Yeah, that's it. That's better actually. Less cumbersome. So that might be useful in a biochemical reaction where you've got bacteria making something like yogurt or some pharmaceutical. Bacteria waste products are acidic.
Okay.
So what you do is you put a buffer solution in which will resist to a point the change in pH. It's not perfect, but it will do it to a point. We don't need to write Ka out again, do we, for that? Because it's the same as Kc. Buffer's different. There's two ways of making them, but what you need is two things. You need a weak acid,
which is going to be our
which will do.
acid. Yeah.
We'll base it on that, but it could be any.
Yeah.
Two, you need the salt with a weak acid. Both in solution. So what salt could we use?
Salt of the weak acid. So that's not perfect.
Yeah. How could we make the salt? Sodium?
Yeah, because So is that? Are we making it from that, or just adding it in?
Well, you'll have to add something in.
Okay.
Because that's not making the salt. That's just making ethanoate ions and H+. How to make the salt? The first one is.
So we just add sodium to it.
Well, you could do that, but that would be a bit. I've seen questions on that actually, but it's a bit dangerous adding sodium to that.
Okay.
It's bad enough adding it to water.
Okay.
So even though it's a weak acid, it'd be too violent. There's two ways. You could just add it. So we could add some sodium ethanoate.
That's not good.
We'd have to buy some. Or you could just make it in the lab, so you could just add sodium hydroxide.
And is that not as?
That'll make it salt. No, that won't be right. Just fizz a bit.
Yeah.
No, it won't. There's no gases given off. So what will it make?
So make your sodium ethanoate and water.
Yeah. You can put the signs on it if you want. You don't have to.
Yeah.
It's really only this bit that we're interested in. So that bit. Okay. What you must do, this must be in excess.
Okay. Is there a reason why?
Yeah. Because if that's not in excess, if that's in excess, all that you're going to do is make this. And we're not going to add that afterwards. That is in the solution that we're making.
Yeah.
So if you had too much of this, all the acid will be gone.
Okay.
And that's not a buffer.
Okay.
Because you need
the acid as well.
You need the acid and the salt of the weak acid.
Okay.
But this time, we can rewrite Ka. Well, it'll be exactly the same, but we need to use it in a different way.
Did you do it for the bottom one?
Yeah, we need the whole thing this time. Okay. You mean the bottom
equation?
Yeah. So it's only Kw where you ditch the left-hand side. So that's on top of the acid. So we make two assumptions.
So we're not including the salt in this one?
Well, that's what I'm going to come to now.
Okay.
And then we'll simplify it more.
Okay.
This time, these two are not equal. Of course they're not. Because you've just you made some salt, or you put some salt in. So that's gone through the roof.
Yeah.
Compared to that.
Okay, yeah.
So we assume two things. We assume same as initial. You assume it's constant. So it'll be the same as it was before you made the book.
Yeah.
We assume that this comes from salt. Some of it will come from the dissociation of this. But we'll assume that that's so small from that. We'll just say that's from the salt.
Okay. So why have we not put the salt in the equation?
Which equation? This one.
This Ka, yeah.
Because the only bit we're interested out of that is this.
Okay. So we're not really interested in the sodium.
We're only interested in that.
Okay.
Now, because these aren't equal, we can't just square that.
Mm-hmm.
But it doesn't matter because we're going to know what we've added.
Okay.
And basically what I would do then is make that the salt, make that the acid, and then it doesn't look so bad. So we've got salt on the top. Acid on the bottom.
Mm-hmm.
That's the undissociated acid.
Yeah. That's
the salt that you've made, and it's obviously times H+. So we can find out the pH of the buffer solution if we've got some numbers.
Okay, why we get the numbers from?
Well, I'll back there, we'll look at an example.
Okay.
If we've got time to just have a quick look at it, I think. Might not finish it.
Worth having a little look at that.
We need to spend a bit more time on this probably, don't we?
Okay, yeah.
I mean, go over it a bit more slowly next time. Does it make sense up to now though?
Yeah, it's making sense.
That's good because this is a topic that people find very, very difficult.
It's slowly like sinking in.
What I'd like to do is to do it before it's done in class, because some terrible damage can be done.
I've not done this in class yet, but the only thing I'm a little bit confused with, so I understand now you're saying that like that's coming from the salt, but we're not too bothered about the sodium, so just bring it in.
Yeah, we'll just forget about it.
I'm hoping it'll make more sense and we put some numbers in.
It will.
Okay, because I'm just So have these not got a thing anymore?
What do you mean?
Like is this you just basically telling me that that's a salt and we're still using that?
Yeah, this will be. Yeah, I've just said that. Well, let's forget about that because it's hardly anything coming from that.
Okay.
I think for ethanoic acid, Ka is 1. I know this one. 1.76 times 10 to the minus 5. Much bigger than Kw. Everything is.
Okay.
Of course. So if we've got everything we need, we can work that out. Find out the pH of the buffer.
Okay.
Or they might say, how would you make a buffer of pH 4 or something?
Yeah.
Like in that case, you'd have to work backwards and rearrange it.
Okay.
But you've never had any trouble rearranging anything. So, right, let's see if we can find this exam question.
I was going to say, for one like this, would you have to get like 3 values?
Yeah, you need at least 3 things to find a 4. I don't think.
Because unlike the other one, you could have 2 unknowns, but just square it. Okay.
That's right. We don't do simultaneous equations.
Okay.
Not for chemistry anyway. So that's an exam paper question. So we could do that one. It's not buffers, but very slightly.
The other product of water is that KW, yeah?
Yeah.
Given by the expression KW value the shape.
So you see how it goes up?
Yeah, temperature, yeah. But then that's just because it's endothermic.
Yeah, okay. All dissociation. Well, yeah, Ka for an endothermic reaction will go up with temperature, and that is endothermic.
Okay, so explain why the expression for KW does not include the concentration of water. So is that basically just because it's just the product? So
it's because it's very large.
Yeah.
And it's constant. Because this is so small.
The concentration of water is large.
Yeah, and it doesn't really change when it gets to equilibrium because hardly any of it dissociates.
Okay.
It's just an assumption.
Okay.
So it's large and constant.
So do you only use KW for water?
Yeah.
Okay.
The W means water, so it doesn't work for anything else.
Okay.
Any other weak acid is Ka.
Okay.
And on the other ones, you have something at the bottom.
Yeah. So that's just for water, and it's because it doesn't properly dissociate, and it's too.
That's it. Yeah, it's a very, very weak acid.
Okay.
So neutral doesn't mean pH 7. It just means that and that are equal.
Yeah.
Right. Why does it increase? Well,
because it's endothermic.
So which way does the equilibrium go?
The equilibrium. So is it the forward reaction that's endothermic?
Yeah.
So the equilibrium will go to the left.
Will it?
No, to the right. Sorry.
It will go to the right. Yeah, to make more
sorry.
product. So it's fine. Have we got a calculation on that? Pure water at 50 degrees C.
Okay, so if you got that value from there,
so you need to square root that.
Yeah, let me just.
And then minus.
I'll just put straight in the calculator. Square root 5.48 10 to the
minus 14.
And then we're minus logging that.
Yeah. So it's going to give around 7, but lower.
Yeah, it's got minus 7.
Well, it's minus log pH, isn't it? Sorry, minus log H plus, not just log H plus. Other than that, it's fine.
So why does it come up minus?
Did you do minus log answer? Yeah. Did you put in 10 to the 14 instead of 10 to the minus 14?
Yeah.
That's why then.
Yeah.
Yeah, it's a very small number, not a very big number.
Okay.
If you're ever stuck, just think, does water dissociate much?
Yeah.
No.
Okay.
Therefore, that will be low. So we've done that, I think. Let's hope there's one on buffers that we can at least have a look at. We can do that. And you could do that with KW.
Are these OCR ones or AQA
That's an AQA
ones?
one.
Okay, I was going to say, I might have a look at these one day.
Yeah, if you go to the PMT Physics and Maths Teacher website, you can get the OCR ones as well.
Okay, cool.
The only reason I'm using this is
because
I know where it is.
Yeah.
You're trying to work out where things are on that thing. So that's great. There's no. I should say there is one, and if not, we can go to one. We've done all this organic stuff here.
We've not completely finished it yet. We split it up. So like one of our teachers does organic, and the other does like the non-organic stuff.
Well, that's what they did when I was in college doing my A levels, but I don't approve of it.
So we're like at the minute we're doing like all like benzene reactions that we just started.
Yeah, I actually think
we've done bits.
I think that all teachers should be made to do all of the topics.
Yeah.
And just alternate from year to year.
Yeah, true.
Because you need to see the whole picture, not just see all little bits. Anyway, so what we could do is find the buffer question. We've got one.
Is this one here?
Yeah.
Right, a buffer solution is prepared using ethanoic acid and sodium ethanoate. So is this pretty much like one we just did?
Yeah.
Right.
So the first thing you do is make some assumptions.
Yeah.
You make that the acid.
Yeah, and that's from the salt.
Yeah, which is sodium ethanoate.
Yeah. But we're not too bothered about that equation.
Well, yeah, you're going to use that equation to find
the
the
pH.
pH.
No, I mean the sodium ethanoate equation.
Not really, because they've already given us.
Yeah, okay. So in the buffer solution, the concentration of ethanoic acid is 0.186. The concentration of sodium ethanoate is 0.105. Okay. So we just assume, will that still be 0.105?
Yeah, that's one of the assumptions we make. We assume that that's just the salt, that none of it came from the ethanoic acid. Mm-hmm. Well, it did when you did the stuff. But
so would you do Ka times 0.186?
Yeah.
And then that divided by, well,
times Ka.
Yeah.
So what it'll be, your H plus, you can rearrange it in as many steps as you like, but it's basically going to be Ka. Mm-hmm. And that's going to go the other way up, so it's going to be acid over salt, isn't it?
Yeah.
It's really easy, this one.
So is that just times, isn't it?
Yeah. So you just put the numbers into there and then minus log it.
Right.
That's the easiest buffer question I've ever seen. And it's just what we need.
Pray for one like that.
It's what we need at the moment.
1, 3, 7, 4 times 10. So minus this time.
Be around 4, you know.
So is it just the acid divided by the salt?
Yeah.
Okay.
So that's the values you're given, 0.186 over 0.104. Sometimes they give it in grams and you have to work out the concentration. Not this one.
So I mean, look. So 4.5.
Right, for a buffer. Yeah. And that's it, really.
Okay.
How you get to this is a little bit complicated. You just have to get used to that being salt. Yeah. But I think you do.
Yeah.
Some people find that very hard to grasp.
Well, I think it helped writing it out.
Yeah, going through it.
Even though we don't use that, I think that helped.
It's so that you're not just saying, well, you just say that that's that.
Yeah.
You know why.
Yeah.
So the only thing that affects the pH in a buffer is this ratio.
Okay.
That's the ratio. And Ka is the constant. And I've got a question, an OCR1 from years ago, and it was about blood. And a patient that had his blood pH was wrong.
Yeah.
And you had to work out what something was. Acid concentration, sodium carbonate, hydrogen carbonate. But that's quite a nice, easy one to start with. So we'll leave it there.
Yeah.
That's okay.
Yeah, that's fine. Can we still carry on a bit with this next time?
Yes.
I'll bring in that question as well. Yeah.
Can you just check if you got that email?
Oh, yeah.
If you haven't, we've got a bit of a problem.
Let's have a look. Just checking. Not come through. Do you want me to give you my school email and see if that will work?
Yes.
Sent to my school email.
Right, just let me go to invite. With the folks now. What that means. Right. Okay.
So it's 13 Higham I.
All small, or is it a capital?
Capital H.
I think that's your one. If you just leave it there.
Do you want me to just write it down? I don't think it.
I better go on to see it.
I was going to say, I don't think it is my mum. I'll try it just here for you anyways.
Well, I'll send it in the chat when you.
That's fine. And if I don't receive it, we'll try and figure it out next time. There you go. I've left it on that piece of paper for you. So it's 13 High Mike, greatsankey.org.
That's it.
Right,
Someone's
perfect.
Just delivered a Christmas tree. I wasn't expecting.
Yeah, Took my time for it as well.
Right, so if I send that to you in a minute,
yeah.
is the case important as well?
Do you know, I don't know. I've always put it as that because it's been like that since year 7. I was going to say, you might as well, because yeah, I would, because I always
So I'll send it you in a minute.
Yeah,
that's fine. We'll just stay on for a couple of seconds and then
perfect.
make sure it works.
Okay,
and if it does, we'll do Monday if you want.
Yeah, that works.
But half an hour, we do a bit more of this.
Okay. Yeah, sounds like a plan. Yeah. Thank you.
Yeah, we're all right for that.
Next time, yeah. One, start on the right.
Oh, no.
2, that's fine. Yeah. All right. Thank you.
I'll send you that thing.